So, hello everyone, welcome back to the fourth lecture of this week. In the last lecture, we had discussed what is PCFG, and we finally came up with what are the interesting problems that we would like to answer. So, for example, what is the most likely parse for a given sentence as per my PCFG grammar, and what is the probability of the sentence as per the grammar. Finally, we also wanted to see how do I learn my PCFG rule probabilities. Okay, if you remember, this was the only difference between context-free grammar and the probabilistic version, is that all the prediction rules here have a probability value. So, how do I learn these values? So, this is what we will be covering in this lecture and the next lecture, and we will be using a specific concept called inside-outside probabilities. Okay, and this will be very analogous to what you studied in forward-backward algorithm in terms of learning parameters for HMM. So, we will go to that. So, starting with the first problem, how do I find out the most likely parse for a sentence? And this can be solved simply if you use the CKY algorithm for PCFG. Okay. So, from the example that we did in the last class, I hope you understand now how to use CKY algorithm for a context-free grammar. So, today I will just show how do you extend that for PCFG. So, let us take an example. So, we have this PCFG. So, what you are seeing here, with each rule you have a rule probability as well, okay. And you can verify that all the probabilities starting from a given right hand side will add up to 1. So, now I want to find out what is the most likely parse for this sentence. The same sentence, a pilot likes flying planes. So, for that I need to find out what is the probability with which I can find a non-terminal S in the final position for deriving this whole sentence 0 to 5. So, we proceed nearly in the same manner as we did in the case of CKY. Okay. So, what I will do, I will just take the same example how we solved CKY, and I will show what are the things that you need to do different here. So, this is what we had seen last time. So, if we have to build if we have to find out what is whether the sentence can derive this whole thing, I will fill it starting from 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, then I will go further. So, I will just tell what is what will differ in the case of PCFG. So, now with each non-terminal, there will be probability with which it can derive that particular terminal or a set of terminals. So, starting from the first element. So, this says that the non-terminal dt derives A. Now, I will write down here what is the probability. Okay. So, if you go to your grammar, the probability that dt gives me A is 0.3. So, I will put 0.3 here. Similarly, for this element, what is the probability that NN gives me pilot, and if I look at my grammar, this is 0.1. Similarly, here what is the probability that VVZ derives likes, this gives me 0.4, and like that I will fill all these entries. Now, this is okay. Now, what I wanted to show is that how do I fill the next entry, that is 0, 2. What is the probability with which the non-terminal NP derives the sequence A pilot? Now, if you remember, a single non-terminal can derive two terminals only via two non-terminals. So, it has to first derive x01, x12, then each of these will individually derive A and pilot. So, how do I fill in this probability value? So, this would be probability that NP derives dt NN times probability dt derives A times probability NN derives pilot. Okay. This probability I can get from my PCFG. So, this probability, if I see in my grammar, this is 0.3. This probability I have already filled in is 0.3. and this probability also I have filled in, this is 0.1. So, the probability that NP derives a pilot here comes out to be 9 times 10 to the power -3, and that is what I will fill in here. Okay. And the same manner you will fill in all the entries. If it is 5, it means the probability will be 0, okay. And if there is a non-terminal here, that means there will be certain probability, and this you can get by finding out probability individually for each of these and multiplying the probability of this rule. So, that way you can incrementally build all this table from in a bottom up fashion, starting from the first element, then the next one, and so on. Okay. So, it will remain nearly same as we did in the last class, only the probabilities and multiplication of probabilities will change. So, suppose you do that for this example, this is what you will find out. Okay. So, these are the rule probabilities that you will come up with. So, I will encourage all of you that you should try this on your own and see that you can get the same set of values that have been shown in this slide. So, now coming to the next question, I am given the PCFG. As my grammar, how do I find out what is the probability of the sentence? Okay. So, one simple solution you can always find is that I find out all the possible parse trees, find out probabilities for each of the parse trees and add those up. That is one way. Okay. But this might be inefficient if there are very huge number of parse trees. If you remember one of the introductory slides, we said that as you increase the number of words in the sentence or the number of phrases, the number of possible passages increase roughly exponentially. Okay. There was something like a Catellan number with which they grow, and it can grow to 100 plus passage. So, you do not want to sum these, get the probabilities individually and then do addition. You want to do something more efficient than that. And how do we do this? And that is where we use this InSide algorithm. Okay. That is one of the main topics of this lecture. So, what is this InSide algorithm? And this is some dynamic programming algorithm based on the concept of inside-outside probabilities. So, now I will try to introduce what is that inside-outside probability. So, this is very central to understanding this lecture as well as the next lecture. So, let us try to understand what is the concept. Okay. And just so that it helps you, this is very similar to the concept of forward backward algorithm that we did in the case of HMMs. So, what is inside outside probabilities? So, again it is parameterized for certain node of my tree. So, what do you see in this figure? I have a sentence with words W1 to Wm, okay, and N1 is the non-terminal. You can think of it as the sentence non-terminal that derives the whole sequence of words using my grammar. Now, I am putting a parameter here, that is Nj. Nj is one particular non-terminal, it can be Np, Vp or so on. So, what I am saying here, assume that there is some non-terminal Nj that derives the sequence Wp to Wq. Okay, and P and Q are arbitrary, you can take any P starting from 1 to m minus 1. Okay. So, what I am parameterizing here is that this Nj derives the sequence Wp to Wq. So, now with respect to that, I am defining what is my inside probability and what is my outside probability. So, you can, as such you can guess this is something outside of that and this is something inside of that. So, how do I define my inside and outside probabilities? So, outside probability is that starting from N1, I can derive the sequence W1 to Wp minus 1, I can derive this non-terminal Nj and the sequence Wq plus 1 to Wm. This is my outside probability. And inside probabilities, given this Nj, the probability that I can derive Wp to Wq as per my grammar. Okay. And it will then follow the same sort of idea that if I can multiply inside and outside probability, that will give me something like the probability of the sentence parameterized by this particular jth non-terminal. So, formally that is how I can write the outside and inside probabilities. Outside probability alpha j pq, that is the standard format in which we write. Pq denotes the sequence Wp to Wq on which it is parameterized, and j denotes the particular non-terminal Nj here. So, the outside probability is probability of generating W1 to Wp minus 1 yes, nj pq and wq plus 1 to m given my grammar. And inside probability is probability of generating wp to wq given nj. Okay. So, this is also parameterized by nj pq because it is deriving w to wq and my grammar. So, that is how I define my inside and outside probabilities. Now, let us take a simple example. I have this sentence, the gunman sprayed the building with bullets, okay, and here your PQ is 4 and 5. So, you are parameterizing with respect to this sequence the building. Okay. So, accordingly this will be your particular non-terminal, that is NP, that is deriving the building. So, now what do you mean by inside probability? So, inside probability is what is the probability that this non-terminal NP at this location derives the sequence the building. This is my inside probability. Okay. And what will be the outside probability here? That is starting from N1, I can derive the sequence the gunman sprayed this NP and with bullets. This is my outside probability. Okay. So, yeah, so this is what we have defined. So, the outside probability alpha NP 4 5 would be the probability of the sequence the gunman sprayed NP 4 5 and with bullets given my grammar, and the inside probability beta NP 4 5 would be the probability for deriving the building given NP 4 5 and grammar. Now, this is just the definition of inside and outside probabilities. Now, how do I actually compute this inside and outside probability given this sentence, and suppose the grammar is also given to me, how do I compute that? So, for inside probability, so let us see, this is the definition of inside probability. Beta j pq is probability of deriving the sequence wp to wq given the non-terminal nj pq and my grammar. Now, so I will be deriving both these probabilities in an iterative manner. So, what will be the base case here? So, the base case here, if you see, would be when p and q are same, that is I am deriving a single terminal from a non-terminal, okay, and that you can find out very easily if your grammar is in the Chomsky normal form. So, what is the particular non-terminal that derives this terminal? So, this would be the base case for deriving a single terminals, and then I will go in a bottom up fashion derive the inside probabilities for higher and higher sequences. So, the base case here is when p is equal to q. So, beta j kk would be probability of w kk given n j kk and g. Now, w kk is a single word, okay, sequence from k to k, and I can immediately find out what is the rule in my grammar that derives this word w kk, and I put this rule probability here, and this will give me this particular probability beta j kk. Now, as an example, suppose here my word is building, okay. So, this is the fifth word. So, I am computing beta for 5 5, and suppose I take n j is equal to n n, the particular non-terminal that derives this word. So, I can compute beta n n 5 5 as the probability with which the non-terminal n n can derive this word building, okay, and this is easily given by my grammar. So, this is my base case. Now, what would be the inductive case? So, I have to go bottom up. So, let us take a generic beta j pq. How do I derive it in terms of the smaller values? So, let us try to do that. So, if I am given, I have to compute beta j pq. What does that mean? It means that I have a non-terminal nj, and that is deriving a sequence wp up to wq, okay, and I have to compute this probability given nj, the probability of the sequence wp to wq. Because I am conducting I am doing it in a bottom fashion, I have to use the lower values. So, I will first say nj can give me some nr and ns. Now, NR will derive from WP to some WT. It is a very generic case. So, this can be any possible NR NS that my NJ can derive, and again NR can go from WP to any WT. So, you can see what can D vary from to. So, D can vary from P up to Q minus 1, okay. And this NS gives me WD plus 1 up to WQ. This is my recursive case, okay. Now, how do I write down this probability? So, I will say this is first the probability that NJ derives the rule the non-terminal NR and NS. So, probability NJ derives NR NS times this probability. Now, here NR is given. So, what is the probability that NR given NR it derives WP to WT? Again you can compute this using, so you can express this using inside probability. So, that is beta R PD. Similarly, this one beta S D plus 1 to Q. Okay. Now, this is for this particular variation that I have shown, but in general D can vary from P to Q minus 1 and they can be any possible NR NS. So, I will have to write down this whole thing, let me call it X. So, I have to say this can vary from P to Q minus 1 and all possible NR NS, okay, and I will put X here. So, this is my inductive step. Now, what do I mean by parameterization over all possible RS and all possible D? So, if you take the case of this simple phrase, the huge building, okay. So, what do I mean by various D? So, if I have this phrase the huge building, by variation of D I mean whether I am composing it by the huge and building or the n huge building, two possible values of D, okay. And what do I mean by parameterization over all possible NR and NS? So, the particular non-terminal that derives this whole thing can be, suppose it is NP, it can come via say NP gives me dt NN, this is one possibility, this is dt and this is NN, or there can be another rule NP gives me dt NNS, this is another possibility. So, this is the parameterization over all possible NR NS and this is over all possible D. So, now we have seen that you can compute it for the only the terminals first and then go bottom up to compute it for other values. Okay. So, now if you do a simple example, so this is again similar to what we have seen earlier. So, I am given this PCFG and this is my sentence and I want to compute the inside probabilities here. So, how do I go about it? And looking at the table you can see that we will be doing something very similar to what we did in the case of CKY algorithm. Okay. But now we will focus on filling up what is the inside probability of deriving this from the particular non-terminal. Okay. So, let us just try to fill in some entries here. Okay, let us try only the first two. This is astronomers and this is saw, okay, and I have to fill in the inside probabilities. So, this would be, so now in the way we defined inside probability, this would be 1 1, this would be 2 2, sequence from word 2 to word 2. This would be sequence from word 1 to word 2. So, now when I define beta j p q, so here p and q are both 1. So, I have to find out what is the non-terminal that derives this word astronomers. Now, if I see my grammar, NP derives astronomers with a probability of 0.1. So, I can fill the inside probability here, beta NP 1 1 1 1 I need not write, I am just writing here, is equal to 0.1, okay, because 1 1 is already defined by the particular cell where we are. Similarly, let us go to 2 2. 2 2 is saw. If I see my grammar, NP derives saw and V derives saw. Okay, so there are two different. So that's where you can see there are two different j that are possible here. So one is beta V, another is beta NP, and this has a probability of 1, and this has a probability of 0.04 using my grammar. Now, suppose I have to fill this one 1 2. What is the particular non-terminal that will derive this whole thing? Again, similar to what we were doing in CKY, is there something that derives NP and NP? If I see my grammar, nothing derives NP and NP, okay, in the right hand side. Now, is there something that derives NP followed by V? Again, there is nothing here, NP followed by V. So, this will come out to be 0. Okay. Suppose there was something that derives NP followed by V. So, I would simply find out what is the non-terminal that is deriving this and put the probability as this times the rule probability. Okay. Similar to what we were doing in the case of CKY for probabilistic and text grammars. The only difference here is that if there are multiple splits for the same non-terminal, I will add all these. Okay. So, for example, the same non-terminal. So, I am taking a hypothetical case. Suppose the same non-terminal x derives NP followed by V and also NP followed by NP with a probability of P1. This is the rule probability. This is the probability of P2. So, I will put here beta x, and this will be P1 times 0.1 times 1 plus P2 times 0.1 times 0.04, and that is how I will fill in all the entries. Okay. So, I will take care of all the possible ways in which this particular non-terminal can derive this. Okay. So, again, so if you keep on doing that, this is what you will see. So, we had filled in this entry and this entry, but I will encourage you to fill in all the entries of this table and see if you can get to this particular term. What is the probability of the sentence generating this whole thing? Okay. So, now if you see this table, you also get the answer for the second question, that how do I find out the probability of my sentence? Use the inside probabilities and compute beta s for 1 to m or 1 to 5 in this case. That will give you the probability of this whole sentence. Okay. So, this was about inside probabilities. Now, how do I compute the outside probabilities? Okay. So, if you remember, it is analogous to what we did in the case of forward backward algorithm. So, now in the inside probabilities we are computing bottom up, and this will be computed top down. And what will be the base case? Base case would be very simple, that is, can I generate the whole sequence 1 to n. Okay. And now, because this is a grammatical sentence we are assuming, so only the first non-terminal, that is sentence, or you can write it as n1, can derive this whole sentence, nothing else can derive. So, that is why the base case will be alpha 1 to m is 1 if the, so this j is 1, otherwise it will be 0. So, if I write down alpha 1 to m will be 1 and alpha j 1 to m will be 0 if j is not equal to 1. So, j is equal to 1 denotes the starting non-terminal. like S or N1, whatever we were using the notation for. So, now this is the base case. Now, what will be the inductive case? So, inductive case would be, I have to compute it in a top down fashion. Okay. So, can you think of the inductive case here? So, now what I am showing here, what are the two possibilities of this inductive case. So, let me just show it quickly on the paper. So, I have to compute alpha j p q, okay, and I am going top down. Now, what is alpha j p q? I have a non-terminal n j that derives w p to w q, okay, and everything else w1 to wp minus 1 and wq plus 1 to wm is there in the sentence. Now, I have to do it in a top down manner. So, I have to use the probability from the upper level. So, I would say what is the non-terminal that derives this n j with some other non-terminal, and again this can be either a left child or a right child. Let us take the case where it is the left child. So, I would say there is some non-terminal n f starting from p up to, let us take some w e p e that derives n j and some n g, and what are the parameters here? This is p q, this would be q plus 1 to e. Okay. So, this is deriving q plus 1 to e. Now, I am doing it top down. So, I have already computed this, that is the probability of this sequence, this and w e plus 1 up to m, this I have already obtained. Now, what I have to obtain in alpha j p q is the probability of w1 to w p minus 1 n j p q and w q plus 1 to w m. This is what I have to obtain. Now, here I already obtained this probability and n f p e and somewhere w e plus 1 to w m. This I have already obtained. So, how do I write it in this in terms of n f p e? I will say this is n f p e, okay. Although there may be different possible n f p e's, we will do the summation over that later, times probability of this rule, probability n f gives you n j n g, already we have come here, and this is deriving w q plus 1 to w e, because I need these probabilities also. Now how do I write down this expression? This we just did in the previous case. This is nothing but the inside probability. Okay. So, this would be beta g q plus 1 to e, okay. And that gives me the probability for this particular structure, although there are various summations that you will have to do. Same case you can do for the when this is the right child, then n g will come here and the situation is very similar. Okay. So, if you look at the inductive case, so this is where it is a left child, this is where it is the right child. In this case, as we did, it is alpha f p e, probability of this rule and inside probability of this whole sequence. And what are we summing over? All the possible f and g's, okay, because it can be any non-terminal that is deriving this and along with any other non-terminal. And what is something else that can vary? My e can vary from q plus 1 up to m. So, I am summing over all the possibilities, and you can similarly see for the second case. So, now so what is important here? You can compute these outside probabilities by using inside probabilities only. So, that means you have to first compute the inside probabilities, use that to compute the outside probability. Okay. Although computing outside probability is much more difficult than computing inside probability if you want to do that on paper. That is why we did example only for the inside probabilities. Now, coming to this point, so remember when I was saying that we have done this parameterization of inside and outside probability such that if you multiply that, we get something interesting that we can use further, and the goal here is also to compute the rule probabilities. That is my third question I was asking, that how do I compute my rule probabilities of PCFG. So, we will come to that in the next lecture. Let us quickly see what do I get if I multiply then alpha j p q with beta j p q. Okay. So, if I do that, so alpha j p q is nothing but probability of w1 to wp minus 1 n j p q and wq plus 1 to m given my grammar, and beta j p q is probability of wpq given n j p q in the grammar. So, we multiply both of these, you will see that wpq can come here and n j p q is also retained, okay, because here I need n j p q to be given, that is already given to me before. So, this is the multiplication. Okay. Now, what does this say? So, it is saying if I multiply alpha j p q with beta j p q, I get the probability of generating this whole sequence of words w1 to wm, and that a non-terminal n j derives wp to wq, okay, given my grammar. Now, suppose I want to find the probability that any possible non-terminal derives from wp to wq. There is some consistent spanning from wp to wq. In that case, I will have to sum over all possible j's, so that I can achieve by summing over all possible j's for alpha j p q beta j p q. This is the probability of the sentence, and that there is some consistent spanning from wp word p to word q. Okay. And this you can also write in this manner. Okay. It is the same thing, n1 derives w1m and npq derives wpq. This and this are the same thing, except this particular index of nj. Now, if we go back to the previous example that we took, what does that mean? So, probability that this whole sentence, the gunman sprayed the building with bullets, and that there is some consistent spanning from word 4 to word 5. That means, there is some non-terminal that derives the sequence w4 to w5. How do I obtain that? This would be summation over all the possible non-terminals nj, such that this happens. The gunman sprayed the building with bullets, njpq given g, and this is nothing but alpha np45, beta np45. So, here I am taking all possible j's. J can be np, vp, and so on, whatever non-terminals. So, I multiply alpha beta for a particular j and add over all the possible j's. That gives me this probability. So, even here it may not be very clear what is the actual use of obtaining this particular probability value. Okay. How do I use it further? And that is what we will see in the next lecture, that how do I use this inside outside probability for learning the rule probabilities of my probabilistic context free grammar. Okay. So, I hope this concept of inside outside probability is clear to you, and then we can see how to use that further in the next class.